So now in section 3, we're learning how to describe the simple harmonic motion. Remember, SHM is simple harmonic motion. So now that we know the cause of simple harmonic motion from previous sections, we can develop the graphical and mathematical descriptions. So I have this picture here from the book, and so we're going to have this ball on a spring in this position right here. That's the initial position when time starts. So time at that point is 0. We're going to let it go, and of course it's going to fall down, and then it'll go back up. So it's just going to bounce back and forth like this, right? So that's the simple harmonic motion. So that is diagrammed out in several positions along the way. So you can actually kind of see with the positions that we have right here that graph, ooh, that looks really good, will look like this graph right here when we're talking about position, okay? So this figure represents the one period of the motion from the start all the way through back to the starting position again. So that's one period, one cycle. The mass moves a distance a above the equilibrium. So here's the equilibrium position right here. We started off a distance a above, which means it's going to drop down to a distance a below. That means the amplitude is a, because we measure from the equilibrium position to the maximum distance away. All right, so our position graph now, the position graph is a sinusoidal function because we see that sine or cosine wave, whatever it happens to be. The velocity and acceleration graphs are also sinusoidal. So we can look at what the velocity graph would look like, and if you had taken calculus, we'd be able to talk about why it looks like that very easily, but because if you haven't taken calculus yet, you don't know the math behind what's really going on here, which is perfectly fine, it's no problem. So when this thing starts off though, like logically, its velocity would be 0, right? So we see the velocity of 0. Now, where is it moving its fastest?
I would say at the one that says Vmax, probably.
Like in general, its maximum velocity will be as it passes through the equilibrium, right? And so that's going to happen right here, and if I draw this down, we see a maximum velocity right there. Of course, it's negative, which is fine. And then here's the equilibrium position again right here. And if I drop that down, again, we see a maximum velocity occurring right there, okay? When is it moving 0? Well, that's going to occur at the extremes when it has reached its amplitude. So at the beginning, in the middle right here, and at the end. So if I drop this one down, I can see that I have a velocity of 0 there. I have a velocity of 0 in the beginning, and also a velocity of 0 at the end, okay? So that's the idea behind the velocity function. Now, acceleration is a little bit trickier to think about if you want to think about it in terms of position. Well, we started off at the beginning and the thing wasn't moving, but which way did it move after that?
Sorry, say again.
So if I'm talking about acceleration, in the beginning, the ball was not moving, but it did start to move. Which way did it move?
It moved down.
So that means the acceleration must have been negative, right? It moved down and it was speeding up. So that acceleration was negative. The velocity was also down and it was speeding up. So that means the velocity and the acceleration had to have the same sign. Okay, and they do. The velocity right now is negative. The acceleration right now is negative. Okay? When it's moving its fastest, at this location right here, from that point on, it's going to start slowing down, right? So its position is on the equilibrium. Its velocity is still going down, so the velocity is still negative, but because it's starting to slow down, because of the resistance with the spring, the acceleration must have started to become positive. And here we are, we're starting to become positive, okay? To resist and cause us to slow down. Now, at the very bottom right here, our velocity is, again, 0, right? We know that, we talked about it. But it's starting to want to move back up, or it's continuing to want to move back up. So the acceleration must be positive, okay? So this is where it reaches its maximum acceleration, when the velocity is actually 0, when the position is actually at its furthest, okay? So basically what's happening here is these graphs are out of phase a little bit. When the position is at its maximum, the velocity is at a 0, and the acceleration is at the opposite maximum. They're out of phase by like 90 degrees or something, okay? So that's what this is talking about here. The velocity and the acceleration graphs are also sinusoidal, but the position and velocity are not in phase, and the acceleration is also not in phase, okay? So they're all slightly out of phase with one another. Okay, so position 1, the mass is at the maximum positive displacement. Describe the position, velocity, and acceleration at key times during one cycle. I just did that. Okay, do you feel like you got it?
Yeah.
Okay. Develop equations for each graph for this scenario. Okay, so we're going to be talking about the equations. Understand that these graphs are for this specific case. So if I started this guy down here instead, well then the position will start off down here. The velocity will start off positive, right? It'll start at 0 but then be positive. So the velocity graph will actually be flipped, okay? And what about the acceleration? Well, the acceleration, because we're starting off down at the bottom and we're starting to move our velocity up, this graph is also flipped. So it will look like this instead, okay? So this is just for this one scenario, depending on what's going on somewhere else. You just have to kind of logic your way into what the graph is going to look like. So, but no matter what, the graph is always sinusoidal, okay? So what equation would we use for the position function right here? What trig function is that?
That would be cosine.
It's cosine. We got to remember that cosine starts at 1, and one full period looks like that. And sine starts at 0, so one full period will be up to that point right there. This is sine. Okay, so for the position function, what is our equation going to be?
Well, let's see here. Sorry, I don't know how to do these. Cosine, so I don't think we have any modifications on the function, so would it just be the function of cosine x?
Yeah, so you could say, like for position, you could say x of t, or because this one is kind of going up and down, you could say y of t if you wanted to, equals, now we have an amplitude, so the amplitude times this looks like a cosine graph, and then times, now we just got to figure out like what the period is and if there's a phase shift going on here, okay? So let me write this down actually. Our typical trig, sine, cosine, whatever, has an A and then sine, could be cosine, bx minus c, and then plus d. Well, d is the center line, so how much have we shifted this graph up and down? Well, if we call the equilibrium point 0, then we didn't shift it at all. So there is no d value in this one, okay? So d is just 0. A is the amplitude, so we have our capital A right there. Whatever our amplitude is, that's that number, okay? Because this is doing what it's supposed to do, so by that I mean cosine is supposed to start up here and then go down, and our cosine graph is starting up here and going down, then we did not reflect it, so therefore it's just a positive A value. Now cosine B, so we need to figure out what this B is right here and this C. So first of all, cosine is supposed to start at its maximum, and our graph did start at its maximum, so that means C is going to be 0 as well. We just have to figure out what the period is going to be. Okay, so the period from beginning to end of the cycle, whatever that time is right there, they said it's capital T. Okay, so we have an equation for period. Period equals 2 pi divided by the letter B. So if I'm trying to plug in the B so that I have that number times x or times t or whatever, then I just need to solve for B here. I know the period is capital T. So I have B equals 2 pi. So I multiply both sides by B, divide both sides by the period, which is T. So in this case, until I know what the period is, I can't do anything more than that. So I would have 2 pi over T. That's the period, and then times time as time goes on. So that would be my equation for the position function. I'll do the same thing for the velocity function. So instead of x position, I would use v for velocity. So v of t this time equals, again, the amplitude is exactly the same. So we have a, and then it's going to be, because we started here and went up, this looks like sine. And then I just got to figure out the b, and that is still b equals 2 pi over t. So we're going to have the same number there, 2 pi over t times our time. There's no phase shift here. It looks exactly as it should. So that's my equation for velocity. And now for acceleration. So what happened in the original? This is kind of confusing now. I have too many marks, so let me get rid of this. What happened on the original?
got a reflection.
It's a reflection. So we have the acceleration of t is equal to negative the amplitude to reflect the graph. And is this a sine graph or a cosine graph?
Cosine.
Cosine graph. We have the period, which is still 2 pi over t times t. Still no phase shift, still no vertical offset, so that's the answer. Okay? All right, so let's move on. The graphs in the table that I just had, so if I go back here, the graphs there, apply to pendulum motion as well as the motion of a mass on a spring. That's why we use the mass on a spring so much. So anyway, a pendulum in a clock has a period of 2 seconds. You pull the pendulum to the right, which is a positive displacement, and let it go. So we call that time right there, t equals 0 seconds. So if I just draw a picture of that, like this is the equilibrium position right here. I pull the pendulum to the right, so maybe it looks like that, and I let it go. Okay, so at what time will the pendulum be at its maximum negative displacement? Well, they told us the period is 2 seconds, right? So that means it will take 2 seconds to go all the way this way and all the way back. So how long did it take to go all the way to the maximum negative displacement?
So then do me 1 second.
Yeah, so part A is B, 1 second. Part B, first have its maximum speed. Where does the maximum speed occur?
The equilibrium.
At the equilibrium point. So what time will it first reach the equilibrium point?
0.5 seconds.
Half a second, that's right. So that will be A for the answer there. Now part C, first have its maximum positive velocity.
Okay, it's maximum positive velocity. It would still be at the equilibrium point, so that would be 1.5 seconds.
Yep, good. We're on our way back to have a positive velocity, so that answer there is C. And then part D, first have its maximum positive acceleration. Tricky.
First maximum. Okay, I think that would be at 1 second because it is at its moved. This is gonna my articulation. So okay, it moved. Now it's at its most negative position, and if I remember correctly, at that point it has a positive acceleration. The greatest positive acceleration because its displacement is the greatest.
Okay, good. So yes, that's correct. The force over here, if we were talking about a spring, the force on this end over here would be at its maximum, which means we would have our maximum acceleration because those are linear proportional quantities, right? So if you think about this a little bit, I just want to explain because it's tempting to say that our first positive acceleration happens as the thing is moving this way because that's where we start to slow down, which means we will have a positive acceleration at this point, but that's not what the question asked. The question asked maximum positive acceleration. So you are correct. That is occurring at what time?
It would be 1 second.
1 second, so B. Good job. Okay, so now the sinusoidal relationship carries forward for all, not just physics, but also like whenever you're doing pre-calc, that type of stuff, calculus, that. So a quantity that oscillates in time can be written like this, and this is exactly what we came up with for the period. Notice the 2 pi over t sitting right there, that's our B value. A is the amplitude, and then we have times 2 pi over t times time, okay? So because we're starting off at the equilibrium point and going in the positive direction, we're talking about a sine that has not been reflected. So we see A sine and then 2 pi over t. Okay, that's a sinusoidal function. If I had this graph right here, I'm starting at the maximum value and then going down. That's just like a cosine graph that's not reflected. So that's why we see A cosine 2 pi over t. Okay, so the argument of the function here, 2 pi over t times t, time, is in radians. So always remember to be in radian mode unless you're given degrees for some reason, which generally in this class doesn't happen, okay? The graphs of both functions have the same shape. So like I could pick this graph up right here and move it directly on top of that graph. It's the same shape, but they're out of phase with each other. Okay. So if x is a sinusoidal function, then x is bounded. It can take only values between positive A and negative A. That's what that means. Okay, so we cannot go outside of that. It's also periodic, which means we repeat. After we go through one cycle, we do the same thing over again, and then the same thing over again, okay? So there you go. Special values, the function x has special values at certain times. So when time is 0 for, I'll just look at the sine graph, we start at 0. When we are halfway through the period, we are back at 0. When we are fully through the period, we're back at 0, okay? Because this sine graph goes up, at halfway through halfway of the period, so 1/4 of the period, we are at our maximum value, and then at 3/4 of the way through, we are at our minimum value, okay? And you should have learned all this already by pre-calculus. With the cosine graph, we know cosine starts at its maximum value, which means at the end of the period, we should be, again, at our maximum value. Halfway through the period, we should be at the minimum value. Halfway to halfway, we should be on the equilibrium, okay? If you can remember it that way, it makes graphing these things way easier. So let's see what happens now. We have an air track glider oscillating horizontally on a spring with frequency 0.5 hertz. What is a hertz?
Hertz, I wrote it down, and it's frequency.
Inverse seconds.
Inverse, yes, gosh. Inverse.
Suppose the glider is pulled to the right of its equilibrium position by 12 centimeters and then released. Okay, so I have maybe a wall, and then a spring, and then my glider on the ground, right? I pull it to the left, 12 to the left. I pull it to the right, sorry, 12 centimeters. So this is the equilibrium position. This is 0.12 meters at this point right here. Then we release it. Where will the glider be 1 second after its release, and what is the velocity at this point? So, where will it be? That's a position, okay? I'm starting off at a positive displacement, so my position function, x of t, has an amplitude of 0.12 meters. Am I dealing with a sine or a cosine situation?
I think because we're starting at, I think it would be cosine. We're starting from our
I would say this is a cosine situation. And then we have our period, right? Something t. What is the period going to be? Do we know?
Tentatively, I don't believe we do.
I believe we don't right now, but we can easily calculate it because we know the frequency. What is the relationship between frequency and period?
They are inverses.
They're reciprocals of each other. 0.5 is 1/2. The reciprocal of that is 2. So the period of this thing is 2 seconds. Okay? So I'm going to write that down. Period is 2 seconds. Now, where will the glider be 1 second after its release? Because I'm dealing with cosine, I know the graph is going to look like this. 2 seconds is over here. So where are we at 1 second in?
We're halfway, so that would be the minimum point.
Yeah. So we're at our maximum negative value from the equilibrium. So for this first part, part A, we're going to say we are at negative 0.12 meters. What is the velocity when we're at negative 0.12 meters?
It would be, oh, that's an interesting question.
We're at our maximum displacement over here. What is the velocity when we're at exactly right there?
Oh, is it just not a numerical value, just its maximum velocity?
No, we can write a number
Okay.
down.
Oh boy, okay.
What was its velocity at this end, at positive 0.12 meters?
Oh my gosh, 0.
Yeah, it's turning around.
Oh.
So for part B, the velocity is 0 meters per second. Okay?
Okay.
All right. So, connecting what we just talked about to circular motion. This is actually the most important thing of the whole deal, okay? Like, it's kind of the thing that you don't get, I think, when you take pre-calculus, because you're just learning, like, okay, I have trig functions, oh, I have circles, like I have this unit circle thing, and the connection between the two is usually lost, which is fine, because you're just learning these skills, right? Well, we need to make the connection now. So imagine you have this turntable, and somehow it's like, maybe it's vertical, okay? So we have this projector sitting here, shining down, and this ball is sitting there, okay? So it's attached to this turntable, and the turntable is spinning obviously like this. So the ball is going around like that, okay? Now the light from the projector is shining down on this ball as it goes around and around and around, which will make a shadow on this screen or table or whatever we do, okay? Well, where's the shadow? It starts off right here at a maximum to the right, and then it will go to the left, and then it will go to the right as the ball moves its way around. Now we're here, now the ball is here, now we're all the way over here, now the ball is there, now we're coming back. Okay, so what's happening here? We have oscillation going on, back and forth with the shadow, okay? At some places, the ball's shadow is going to seem to be moving the fastest. At some places, the ball's shadow is going to seem to stop. So when we're at this end over here, the ball's shadow will seem to stop. When we go to this end, the ball's shadow will seem to stop. Okay, so when we're going this way, do we seem to be moving the ball's shadow the fastest? Right here in the middle, at the equilibrium position, okay? So that's the connection. Now, if this ball was actually flat, if this table was actually flat, and this screen was like vertical, okay, and the projector was sitting off to the side, shining horizontally onto that ball, it would be the same idea. So now I've set it up over here, right? This ball's shadow is going to go from here up, stop, turn around, come back, stop, turn around, come back, stop, turn, okay? So there's oscillating motion going on here too. So we have periodic motion in the X direction, and we have periodic motion in the Y direction as well at the same time, okay? So when this ball is right here, let me change colors real quick. When this ball is right here, in the X direction, we would see the shadow right there, but in the Y direction, we would see the shadow right there, okay? What corresponds to X and what corresponds to Y? Cosine corresponds to X and sine corresponds to Y, okay? So let me clear this real quick and show you what I mean by all that. So I'm just erasing all this so that we have some clear ability to see. So in the X direction, if that ball is sitting right there, actually let me start it right here. The ball is sitting right there. Where's the shadow at? All the way at the extreme, right? Now, but in the Y direction, where's the shadow at?
Midway up.
Midway, okay?
Oh,
now, we're gonna
okay.
rotate this thing around. Where's the shadow when we reach right here in the X direction?
Midway.
Midway. Where's the shadow in the Y direction? At the extreme, okay? So if I draw a graph of that in the X direction, we started off here. In the X direction, it was at the minimum value or the maximum value or whatever you want to say. I'll put it right here. If we were in the Y direction, where were we? On the horizontal, right? At the 0. Okay, now we went to here. So in the X direction, we went to the center. In the Y direction, we went to the maximum. In the X direction, now if I go here, now we're all the way over here in the X direction, which means we're at the extreme other end. In the Y direction, where am I? Back on the center line. Okay? Now, if I go down to the very bottom, where are we in the X direction? Back at the middle. And then where are we in the Y direction? At the extreme negative end. And if I complete the full period, where am I back at the very beginning right here? Back where I started. Up at the top here, and back on the center line here. Now, if I graph that, cosine curve, sine curve. Which one was I graphing here? The X. So cosine corresponds to the X coordinate, and this one was the Y coordinate. That's sine. Sine corresponds to the Y coordinate. And that's why, when you're taking trig, you realize that cosine corresponds to the X coordinate and sine corresponds to the Y coordinate, but you don't really make that connection. Because actually what you're doing is you're graphing circular motion as time goes on. One of them is in the X direction and one of them is in the Y direction.
Wow.
Okay? Kind of cool, right?
Yeah, really.
All right, so that's the simple harmotion of the block as well. This block is moving back and forth. Just like this ball is going around and around, this block is moving from one extreme to the other and back, and then back, and then back. So it's basically the shadow of the ball. It's the exact same math. Okay? All right. So now we have a bunch of stuff on here. So let me see if I can explain this pretty well. For projections of position, velocity, and acceleration. So we're talking about exactly what I was just talking about, where we have circular motion going on, and I want to look at the projection of the shadow of the ball, okay? So in part A, the particle is in uniform circular motion, so it's going around this circle at a constant speed all the time, okay? We have this angle sitting right here, whatever that angle is. Now, what we want to do is come up with the x component of the particle so that I know how far away from equilibrium that shadow is, okay? So how do I come up with the x component here? I need to use this angle. This is the adjacent side, so it's the amplitude, whatever this radius is here, times the cosine of that angle because of trig, right? Adjacent over hypotenuse. Okay, now if I want the x component of the velocity, okay, well the velocity, as the ball moves around in this direction, the velocity will be always tangential to the path, right? So tangential to the circle itself. Okay, so the velocity we know from before is going to be 2 times pi times the frequency times the amplitude. That's the radius, okay? So I will need to find the component here. So this angle, the magnitude of the x component is v sine that angle. So you could use theta. You don't have to use their Greek letter. It's fine. So let's say we're talking theta. So v is here. Sine theta, how come it's sine theta?
Because we have to do opposite and hypotenuse.
Well, sine theta is opposite over hypotenuse, but how come we're using opposite over hypotenuse?
Is it just because we're just looking for that opposite side? Or is that to just not, is that just lateral thinking that I'm doing there?
This vector right here stops right there. So this angle right here, they're saying is, nope, that's not it either. So what is it? How come it's sine? So we could remember that position and velocity are out of phase with each other. So it can't be cosine if we just use cosine, so it has to be sine. We could think of it that way. But basically what you need to do is always create the right triangle. So like we created this right triangle right here. If I wanted the y coordinate right there, then I would use sine. If I want the x coordinate, then I'm going to use cosine. Okay. And then finally the acceleration. So we know that in circular motion, the acceleration is always towards the center of the circle. So now our vector is here. So the magnitude of the x component of the acceleration, because I'm talking about x here, is going to be the acceleration times the cosine again, because we're talking about that guy right there. Okay? They're back in phase, but reversed, so flipped. So the velocity vector can be calculated can calculate the particle speed in the x direction. Vx equals negative velocity times the sine of theta, or we could say v is 2 pi times the frequency and then times the amplitude sine. So we wind up with this equation right here. The maximum velocity is 2 pi times the frequency times the amplitude. And then from this third figure, the acceleration, we can get a maximum acceleration by doing that math there, and it's not worth explaining probably. We just have those formulas that we can use. So if we know the amplitude and the frequency, basically the motion is completely specified. We know the position, we know the velocity, we know the acceleration at any time, as long as we know those two things. Okay, so the position, velocity, and acceleration of objects undergoing simple harmonic motion are sinusoidal, as we know, whose amplitudes and phases are related in a particular way, based on basically exactly what I was just talking about. For the position, we have this equation. For the velocity, we have this equation. For the acceleration, we have this equation. The maximum values of the displacement, velocity, and acceleration are determined by the amplitude and the frequency. So the position, the maximum position is just the amplitude. The maximum velocity is 2 pi times the frequency times the amplitude. And then the maximum acceleration is 2 pi times the frequency. That's squared times the amplitude, okay? And the math to get there was on the previous slide. We don't need that math necessarily, we just need to know these ultimate formulas here, okay? And then also the graphs themselves are out of phase, but they're all sinusoidal. Whether it's cosine or sine, doesn't matter right now, they're all sinusoidal, okay? So, the John Hancock Center in Chicago is 100 stories high. Have you seen it? Do you know which one that is?
Never been there.
Okay. Strong winds can cause the buildings to sway. We've talked about this before, as is the case with all tall buildings, and they're designed that way. They know that they're going to sway, so they design them to do so. On particularly windy days, the top of the building oscillates with an amplitude of 40 centimeters, roughly 16 inches, which is quite a bit, really. If you're at the top, you're moving back and forth that much, and you can feel it too.
That would be scary.
And a period of 7.7 seconds. So you're moving back and forth one full time, and it only takes 7.7 seconds to do it. You're gonna feel it. So it's like kind of being on a rocking boat. What are the maximum speed and acceleration of the top of the building? Okay, so we know we have an amplitude of 40 centimeters, okay? So that means we're going this way 40 centimeters, and then that way back, so back to 0, and then another 40 centimeters this way, okay? Now, that period to here is 7.7 seconds. So what are the maximum speed and acceleration? So I'm just going to go back a little bit right here. We already know X max. We know the amplitude. V max, 2 pi times the frequency times the amplitude. So what is the frequency?
The frequency is, period of 7.7 seconds. So
Frequency is related how to the period?
it is you said reciprocal. Yeah,
Yeah.
reciprocal of the period. There we
So the frequency is 1 over 7.7, whatever that number is, and then the units now are inverse seconds.
go. Okay.
Okay, so we know everything we need to know. V max is 2 times pi times 1 over 7.7 inverse seconds times the amplitude, which is,
Where am I at here? 40 centimeters.
so 0.4 meters. What do we get?
All right. I think I should be fine. 0.326399.
3263, blah, blah, blah. Do we like that?
We do not.
Okay, what do we like?
We've technically got one significant figure.
I kind of agree with you, but let's call it 2, so 0.33.
Yeah,
What are the units here?
that would be meters per second.
Correct.
That's not insignificant.
No, it's definitely not. You're moving. Okay, and then the second part, what is the maximum acceleration? So, acceleration max, we go back here, and we have this formula right here. 2 pi f squared a. Okay, so we have 2 times pi times the 1 over 7.7 inverse seconds. This is squared times the amplitude again, 0.4 meters.
Okay. 0.266341.
Blah, blah, blah. And we're going to keep 2 again, so 0.27. What are the units here?
That would be meters per second squared.
Right. Okay. Not insignificant.
No.
You can definitely feel it. Not so much towards the bottom of the building, but at the top, most definitely. And then just imagine like the Burj Khalifa or something
Oh,
that's,
yeah.
you know.
Do they, I don't know anything about that building, do they have offices up that high?
I don't know. I'm not sure what's in that building or where or what. And the way that it's built, it may not sway nearly as much because, you know, if you look at how it's built, it's kind of different. But then you have these people that are trying to build a mile-high building and stuff. Like, how much is that going
yeah.
to sway? You know, if I'm at the top of that building, I probably would freak out.
It'd be like a roller coaster.
Yeah, it would. Okay, so the classic children's toy consists of a wooden animal suspended from a spring. If you lift the toy up by 10 centimeters and let it go, it will gently bob up and down, completing 4 oscillations in 10 seconds. Okay, so I'm going to draw a picture of that. We have the ceiling. It's attached by a spring. We got the children's toy, whatever it is. It's your basic spring and mass system, okay? So we know that we're going to lift the toy up. So here's equilibrium. We lift it up by 10 centimeters. And we let it go, so then it's going to bob up and down. Okay, great. Completing 4 oscillations in 10 seconds. They're telling us something there.
Mm-hmm.
What is the 10 centimeters?
The 10 seconds?
The 10 centimeters.
Or the 10 centimeters. That is our amplitude.
Yep. So A equals 0.1 meters. Now, the only other thing that we have to figure out is the frequency. So this information, 4 oscillations in 10 seconds, tells us the frequency. We just got to calculate it.
Mm-hmm.
So how do I calculate it?
Okay, would we do 10 divided by 4 to get number of units of time?
4 oscillations in 10 seconds. How many oscillations do I get? How many seconds does it take to get 1 oscillation?
Oh, okay, so then it would...
Or, better yet, how many oscillations do I get in 1 second? Per second, right? So all you got to do is take these two numbers and divide them. 4 oscillations in 10 seconds. So that's 0.4.
Yeah.
0.4, and the units are inverse seconds. 0.4 oscillations per second. Okay, so now we have everything we need. What is the oscillation frequency? You just found it. When does the toy first reach its maximum speed, and what is the speed? Okay. When do we get its maximum speed first? We pushed it up to here, and we let it go.
So then it would get its maximum speed once it came down to its equilibrium point.
So what is the period of this?
It would be, so...
It'd be the reciprocal of 10 over 4. 4
Yeah.
over 10, right? It would be
Yeah.
10 over 4. So 5 halves.
Okay.
So 2.5.
I want to say seconds.
2.5 seconds. So the period is 2.5 seconds. Now, when does the toy reach its first reach its maximum speed? So its first maximum speed will be when it gets down to the equilibrium, right?
Mm-hmm.
So halfway through the period would be what time?
1.25 seconds.
1.25 seconds. So that's like 5/4, right? So halfway to halfway, we'll reach our equilibrium point. What time is that?
I want to say like 0.815, but I'm going to actually...
Would be 5/8.
5/8.
So that's 0.625 seconds. So that's the answer. And what is the speed? What do we do?
Okay, I think we can grab our velocity formula.
So our velocity formula is this guy, 2 pi FA. So V max, 2 times pi times the frequency, 0.4 inverse seconds, times the amplitude, which is 0.1 meters. What do we get?
.251327.
So we'll keep 0.25 meters per second. Okay, part C. What are the position and velocity 4 seconds after you release the toy?
All right.
How can we find position?
The position is just our amplitude.
Is it?
Is it? Apparently it's not. Oh, that's our X max.
So the period is 2.5 seconds.
Mm-hmm.
So 4 seconds in, we've gone through one full cycle. We have another second and a half to go, right? Okay. So halfway through the period is 1.25 seconds. So we've gotten all the way to the bottom again, and we're starting to come back the other way. So our position should be, if this is positive 10 up here, our position should be some kind of negative, pretty close to 10. Does that make sense?
Yeah.
And then our velocity should be what?
Near zero.
But positive or negative?
Would be
Should be positive-ish, near zero-ish, right? Okay, so let's go back and see if we have a formula for position. Right here, x max is a amplitude, but the position itself is this equation right here. Okay? So amplitude times cosine 2 pi ft. So x at 4 seconds is equal to the amplitude, which is 0.1 meters, times cosine times 2, or not times, cosine of 2 times pi times the frequency, which was 0.4 inverse seconds, times time, which was 4 seconds. Seconds times inverse seconds divides out, so we're left with a unitless thing for cosine, which is good, we needed that. When we're left with just meters, what do we get?
All right. Radian, not degree.
Yeah, radians.
Okay. Negative 0.080902.
0809, so 081 meters, right? Now, is that what we thought?
Yes.
Something below the equilibrium point? Yes. Okay. Pretty close to 10 centimeters, right? 8.1 centimeters. So yeah, that makes sense. Okay, now what is the velocity at 4 seconds? So again, we have a velocity equation, not velocity max, but this one. So it's negative V max times sine 2 pi ft. So we need to figure out, oops, V at 4 equals negative V max. Do I know what V max is? Sine 2 pi times the frequency, which is 0.4 inverse seconds, times time, 4 seconds. But what is V max?
Well, unless we can figure it out using logic, we can use our formula.
Yeah, what's our formula?
Okay, 2 pi fa.
Okay, so I'm going to switch this to negative 2 pi times the frequency, 0.4 inverse seconds, times the amplitude, 0.1 meters. So we have meters per second on the outside, and then no units on the inside of sine, so we're good. We're going to wind up to meters per second. What is our answer?
You might want to pause, it's going to take me a while.
0.14277. So what are we going to call this? Is that what we said? 0.14277? Or is it 727?
I'm sorry, 0.1477727.
7727, okay. So then if we go to 2 decimal places, this is going to be 0.15 meters per second, and we're done. Okay, one last thing to do. The figure shows 4 identical oscillators at different positions, different points in their motion. Which is moving the fastest at the time shown?
Okay, so yeah, they all have the same equilibrium point. So I would say A.
Because?
Because it's at the equilibrium.
That's correct. They're all moving, therefore this guy here is moving its fastest because it's going through the equilibrium point. Good job. That's the whole section.